Hello everyone. Today we are going to go through magnesium and its alloys lecture 2. I hope you already have a basic picture of magnesium alloys after the first lecture. If you have any questions, please feel free to drop me an email. Right, in this lecture we are going to cover the following topics. First, we need to understand the classification of magnesium alloys. Otherwise, we don't know what alloy elements are in a specific magnesium alloy. Second, I will shortly introduce the effects of individual alloy elements in magnesium alloys, which will give you a big picture why some alloy elements are added in some alloys. Third, we need to go through some binary magnesium alloys phase diagrams. Phase diagrams are very important, not just in magnesium alloy systems, but also in other alloy systems. I believe you have already touched lots of titanium or aluminum phase diagrams with other tutors. Phase diagrams are very useful to predict and identify the phase evolution, which can be used in designing new alloys. During the whole lecture, I will show you some commonly used magnesium alloys and their applications. First, let's just imagine that you come across a magnesium alloy, AZ31B, in a publication. If you do not know the classification, you will have no idea what element and their amount in this magnesium alloy. The International Magnesium Alloy designation is based on the American Society for Testing and Materials, which is called as ASTM. Generally, the alloys are named with two letters, indicating the main alloy element, followed by two numbers, illustrating the nearest nominal weight percent of each of the two additions. First letter represents the highest amount. Second letter represents the second highest amount. A third letter may be needed to indicate the stage of development of the alloy, A, B, C. This table shows the K letters represent major alloy elements used in magnesium alloys. For example, A is short for aluminum, C is copper, E is rare earth metals, K is zirconium, M is manganese, Q is silver, S is silicon, Y is yttrium, and Z is zinc. In addition, a fabrication code, for example, F as fabricate, H string hardened, is added to indicate the condition of alloy. Heat treatment designation used in magnesium alloys shares the same identification system with aluminum alloys, as shown in these tables. It should be noted that temper H and T have several subdivisions. For example, H1 is string hardened only, T4 is solution heat treated, T6 is solution heat treated and artificially aged. T4, T5, and T6 are commonly used in metal and alloys. Now let's have some examples. The first one is AZ92A. The magnesium alloy contains 9 weight percent of aluminum and 2 weight percent of zinc. Another one is QE22A T6. This alloy contains 2 weight percent of silver, 2 weight percent of rare earths, and in the A modification. T6 indicates the alloy is solution heat treated, quenched, and artificially aged. It is an aging hardening alloy. This table lists the effects of main alloy elements and impurity on magnesium alloy's performance. I will choose some elements as examples. Silver can improve strength and grip properties of magnesium alloys at elevated temperature, especially with the existence of rare earth elements. However, the corrosion resistance of silver-containing alloys is not very good. Aluminium is commonly used to improve castability and precipitation hardening. Uranium is rarely used because it is poisonous and rare. Calcium has been popular recently because it can refine the grains, improves grip properties, and it can weaken the strong basal texture like rare earth elements. Copper, iron, and nickel are not friendly to magnesium alloys, since they normally deteriorate the corrosion resistance even with a very small amount. However, copper and nickel can be used to develop magnesium mechanical glasses. Lithium can further decrease the density of magnesium alloys, and it can introduce a BCC beta phase in magnesium alloys and improve the ductility of magnesium alloys, but the corrosion rate is higher than other commonly used magnesium alloys. Rare earths, yttrium, and thorium can significantly improve the mechanical properties of magnesium alloys, especially for high-temperature applications because of stable precipitate and second-phase particles. They can also improve the ignition temperature and reduce the potential fire risk. Thorium was used during the two world wars, and now the use of thorium has been reduced significantly because it is radioactive. Silicon can form stable silicide compounds, but it decreases castability and formability. Tin recently has been widely used as solid solution hardener in new magnesium alloys. Magnesium strontium has been studied as a potential biodegradable material with excellent bioactivity to promote the bond formation. Zinc is one of the commonest alloy additions. It can improve precipitation hardening. Last but not least, zirconium is the most effective grade refiner, but it cannot be used with the presence of aluminum, silicon, and manganese, because they normally form stable particles with zirconium first in the melt. Aluminum is one of the most important alloy elements in magnesium. Several systems contain aluminum up to 10%. For example, AZ, AE, AM, and AS alloys. This figure shows the magnesium-aluminum phase diagrams. As we can see, aluminum can be easily dissolved in the magnesium matrix. The solubility limit is 12.7 weight% at around 436 Celsius degrees. Above the solubility limit, orbital intermetallic Mg17Al12 forms out from the matrix. The solubility limits of aluminum at the eutectic temperature 436 Celsius degrees is around 12 mass percent and falls to about 1% at room temperature. In theory, the Mg17Al12 should have a strong aging hardening response. However, the strengthening effect is not high as we expected. The main reason for this is that Mg17Al12 is coarse and normally forms on the basal plane, which cannot hinder the dislocation movements effectively. The figure also shows a phase evolution of magnesium-10 weight percent of aluminium alloy. When the temperature cools down to 598 Celsius degrees, it starts to solidify and magnesium comes out from the liquid melt. Below 470 Celsius degrees, all the liquid turns into solid magnesium. However, from 308 degrees to room temperature, Mg17Al12 precipitation happens. Thus, after casting, this alloy has two phases, magnesium and Mg17Al12. This figure plots the tensile strength of several magnesium-aluminium-based alloys as a function of temperature. It is very clear that the strength of all the alloys decreases quickly when the temperature is over 100 Celsius degrees. This could be due to the thermal activation of dislocation motion, resulting in either plastic deformation at higher temperatures. For example, more dislocation systems will be activated at high temperature, as we mentioned before in the lecture 1. The left image gives a typical casting AZ80 alloy microstructure, and the white colored phase in this microstructure image is Mg17Al12 phase, which are continuously distributed along green boundaries. However, the right image shows the Mg17Al12 phases were discontinuously distributed due to a more slowly cooling rate. Due to its good castability and low density, magnesium and aluminium alloys have been used in many applications, especially for automotive and aircraft industry sectors. For example, the left image shows a AZ91 gearbox housing in the Volkswagen Passat, and the right image is a picture of a seat frame made of die-cast AM20 and AM50 used in Benz Roadster. Zinc is an important alloy element, but rarely used as a major alloy element. It is usually used with other elements like zirconium, manganese, or rare earth elements. For example, the ZK, ZH, ZM, ZC, and ZE series of alloys. The reason for this is binary magnesium-zinc alloys are not amenable to grain refining by superheating or inoculation, and are prone to microporosity. As a consequence, they are not used for commercial castings. The binary magnesium-zinc phase diagram shows a eutectic at 51.3 mass percent. There is 6.2 mass percent solubility at the eutectic temperature. Thus, zinc also has a positive response to age hardening in magnesium alloys. Magnesium zinc can be easily formed from oversaturated magnesium matrix, and magnesium zinc 2 can form from GP zones with suitable heat treatment. In these magnesium AZ zinc alloys, we can find there are two main precipitates. One type has a rod shape, while the other one has a plate shape in both alloys. However, the density of precipitates is much greater and more uniform when a tiny amount of cobalt is present in the right image. Thus, minor additions can modify precipitation in magnesium zinc alloys. Other elements like calcium and strontium can accelerate the rate of aging but delay overaging, refine the sizes, and increase the number density of precipitate. Zirconium is a very effective green refiner for magnesium and can be used with all alloys except those containing aluminum or manganese. Zirconium is a good refiner because it has the same crystal structure and the lattice parameters are virtually identical. The phase diagram shows the solubility of zirconium in magnesium is 2.7 mass% at the melting temperature of magnesium and decreased to 0.2 mass% at room temperature. Thus, during cooling, zirconium could form heterogeneous nuclei for magnesium alloy to solidify on. Let's see a green refinement example. The next image is pure magnesium, and its average grain size was 750 microns. Under the same cooling conditions, after adding only 0.56 weights% zirconium, we can see the average grain size in the right image was substantially decreased to 50 microns. Due to its great refinement ability, zirconium was added into magnesium zinc alloys such as ZK51 and the higher strength ZK61 that are normally used in the T5 and T6 tempers, respectively. However, the fact that these alloys are vulnerable to microporosity and are not weldable because the melting temperature of zinc is very low. These issues have severely restricted their practical application. Further to magnesium zinc zirconium alloys, rare earth elements can be introduced to form magnesium rare earth zinc zirconium alloys. These alloys contain either the neodymium mystery metal or the cheaper cerium-based mystery metal. Castability does not present any problems because of low melting point eutectics formed as networks in grain boundaries during solidification. Aging introduced precipitates within the grains, and the generally good creep resistance in these alloys is attributed both to the strengthening effects of these precipitates and the presence of the grain boundary phases. For instance, we can see the grain boundary phases and the precipitates in the image of alloy AZ33 after aging at 350 Celsius degrees for 8 hours. One commonly used alloy is ZE41. Magnesium 4.2%, zinc 1.3, Ce and 0.6 the coulomb that develops moderate strength when given a T5 agent treatment, which is maintained up to 150 Celsius degrees. As shown in the figure, one application has been helicopter transmission housings. This is another image of sand-cast helicopter transmission made of ZE41, and the cover was made of WE43, which we will talk later. We can see the weight could be around 100 kilograms, but it can be up to 450 kilograms if steel is used. So again, the application of magnesium alloys can make a huge difference to reduce the cost in aircraft industry. To further extend magnesium alloys application to aerospace, the alloys need to have good mechanical properties at high temperatures. Several commercial compositions were subsequently developed having tensile properties which exceeded those of any other magnesium alloys at temperature up to 250 Celsius degrees, and were comparable to the high-strength aluminum casting alloys. The most widely used alloy has been QE22. Alloy QE22 has been used for a number of aerospace applications. For example, aircraft landing wheels, gearbox housings, and helicopter rotor fittings. Its superior tensile properties over most magnesium alloys are maintained to 250 Celsius degrees. Another commercial high-temperature magnesiums are magnesium-etching rare earth alloys. For example, WE43 has been developed for improved elevated temperature tensile properties. Thorium is best known to improve high temperature properties due to its significant aging hardening response and great refinement effect. However, it is slightly radioactive, which makes thorium-containing magnesium alloys not commercially available. QE22 contains 2.5 weight% silver and 2 weight% rare earth elements such as neodymium. The phase diagram shows the solubility of silver in magnesium is 15 mass% at a temperature of 465 Celsius degrees and decreased to nearly 0% at 200 Celsius degrees. So it has an excellent age hardening response at high temperature. If these alloys contain less than 2% silver, the precipitation process appears to be similar to that occurring in magnesium rare earth alloys and involves the formation of magnesium neodymium precipitate. However, for higher silver contents like 2.5% in QE22, silver can modify precipitation sequence and increase the volume fraction of particles that are formed. However, the precipitation sequence in these alloys has not been clearly identified. Maximum age hardening and creep resistance are associated with the presence of nanoprecipitate in the microstructure. This figure clearly shows that the dense and fine nanoprecipitate can be formed in the QE22 alloy after peak aging at 200 Celsius degrees. As mentioned before, QE22 alloy is used in the aerospace industry, particularly for applications at elevated temperatures. These two images show QE22 castings can be used in accessory drive gearbox of the F-16 fighting Falcon. E-trim is an element with a high solubility in magnesium and has a big potential for edge hardening. Solubility limit is 12.5% in the phase diagram. The purpose of the neodymium is to form stable precipitate. When magnesium is alloyed with yttrium and rare earth elements like neodymium, these alloys have better high temperature strength and creep resistance than QE alloys, and furthermore, better corrosion resistance properties. This results in the WE alloy series. WE43 can maintain room temperature, tensile strength of 250 MPa after long-term exposure at 200 Celsius degrees. It should be noted that yttrium is expensive and difficult to be melted as pure element. Yttrium containing bismuth metal or magnesium yttrium master alloys are used for developing the WE alloys. For example, WE43 consists of 4% yttrium, 2.25% neodymium, 1% heavy rare earth, and 0.3% zirconium. Due to the high cost of some of the alloy elements and processing, WE alloys are mainly used for defense, military aircraft, and specialized applications. For example, here we can see the WE43 casting box, which have been used in MD helicopters MD600. This slide summarizes the mechanical properties of high-temperature magnesium alloys, including WE and QE alloys and other ZE, EZ, HK alloys. We can say WE alloys have much higher yielding strength in high working temperature, up to 250 Celsius degrees, and their yielding strength were quite stable and high after exposure experiments at 250 Celsius degrees up to 10,000 hours. Lithium is the only alloy element which decreases the density of magnesium. The phase diagram shows eutectic at 588 Celsius degrees with a solubility limit of lithium in magnesium of 5.5 mass%, which is largely retained at lower temperatures. The second phase beta BCC is also stable down to room temperature, opening the possibility of producing alpha plus beta and beta workable alloys. As shown in the phase diagram, only about 11% lithium is needed to form a full beta phase magnesium lithium alloy. A number of Rhodes alloys were developed in Russia, including two designated MA18 and MA21. MA18 has a BCC lattice, whereas MA21 has a mixed HCP and BCC structure. These alloys are also wettable, and some properties are summarized in this table. Generally speaking, Both alloys have lower strength but higher elongation. When HCP phase exists in Ma21, the strength is increased while the ductility correspondingly decreased compared to pure BCC phase in Ma18. Okay, this is all for today. Thank you very much. See you soon.